everybody. I'm going to go over the synthesis of imines and enamines in this video. So we're going to talk a little bit about the mechanism and kind of introduce how we can think about these carbonyl reactions with weak nucleophiles, which are the neutral nucleophiles. So first, just to start off a bit of nomenclature, because we probably are not that familiar with these. So the structure on the left is an imine. Okay, you can essentially think about that as the nitrogen equivalent of a ketone. And then on the right is the enamine. Okay, essentially the nitrogen equivalent of an enol, right? So ene, alkene, amine, an amine on an alkene. Okay, so we get these two different products by using very similar reaction conditions. It's just a change in what kind of amine you're actually using. So over here, we've got a primary amine, and that's getting us to the imine. And if we use a secondary amine, that gets us to the enamine, okay? So we're gonna need to make sure that we're very careful about identifying which one you have so that we kind of know what's going on in terms of the mechanism. So let's do the imine first. So the first section, Okay, so the first step of the mechanism we've got a ketone, this is methylamine, and we've got H3O+. Okay, so hopefully by now I've kind of burnt it into your brains that if you have an acid, the first thing that you should do is protonate something. So we think about what is the most basic atom here. That one's pretty good because it's resonance stabilized. So that oxygen is going to be what we're looking for. So let's go ahead and protonate that oxygen. So then we have this. So at this point, the energy difference here between starting materials versus reactants, I said those backwards, but you know what I meant. So starting materials and products is not that different, right? Because really we're looking at these things, not a ton of difference there. Like there's not wildly huge differences. And so we've seen it before when we have an acid-base reaction, we can use the equilibrium arrows. So we're going to be using equilibrium arrows for this whole process. Keep in mind that since we're using the weak nucleophiles, we're going to be using reversible reactions. So if you need to, go ahead and look at the other video on reversible reactions. So all of these products versus starting materials are not super different in energy level. So because of that, they can actually go back and forth. When we get to the end of this mechanism, we're going to talk about how we can try to get all the way to the product or all the way to the starting material, depending on what you want to do. So once we get to this protonated carbonyl, then we're ready for our nucleophile to come in. Okay, so I've got my nitrogen with my methyl group on it. This is going to look exactly the same as the other carbonyl nucleophilic reactions that we've seen before. Okay, so at this point now, let me fix that, that's bad. My nitrogen is now positively charged. Okay, so again, don't have huge energy differences going on here. So at this point, if I'm trying to get to an imine structure here, we need to figure out how am I going to get a double bond at that nitrogen. This obviously needs to leave. The best way to make it leave if I'm in acid is to protonate it. But to do that, we probably want to deprotonate the nitrogen first. Okay. So we can bring in water, which is going to be our base if we're in H3O+. Deprotonate that. to get to a neutral structure. And then we can go protonate to make water. And now we've set ourselves up for a good leaving group. So this should look very similar to some of the carbonyl reactions we've done so far with the strong nucleophile. So like think about it like adding a Grignard to an ester, where you make kind of an intermediate carbonyl along the way. The only difference that we're having to deal with right now is that since we're not in a strong base, which is like a Grignard or a lithium aluminum hydride or organolithium, since we're not in a strong basic conditions, we're in acid, then we need to just consider some proton transfer steps before to make sure that we're not trying to kick off an OH minus into an acidic solution. So that's why we're going to protonate our leaving group before we kick them off. But this is still the same kind of tetrahedral intermediate that we saw with the Grignard additions. So now we're going to use the nitrogen lone pair to move that down, kick off our leaving group. And then we get to an iminium ion. Okay, so the iminium ion is an intermediate along the way here. Not our final product, as we can see from what we had up above. The only difference is that I need to have water, deprotonate that nitrogen, just a simple acid-base reaction, and I get to my final imine product, okay? So if we are thinking about how are we going to kind of pull this to the starting material or the product. So keep in mind that if you throw that in with water, you can get back to your ketone. If you throw this in with your amine and your acid, you can get the amine out. So we can make either one from either of them. So we need to think about how are we going to actually convert it to product or convert it to starting material, depending on what you want. So because we are forming water in this reaction by this right here, if we have a way to remove water from the reaction, then I can start kind of pulling on the equilibrium using Le Chatelet's principle. And if I start taking away that water, take it out, that means that the reaction is going to work harder to produce more of that to maintain equilibrium. So if I remove water, I'm going to favor the products. And if I add water, I'm going to favor the reactants. Okay, because essentially what we're saying here is we can go through this entire process backwards. It's going to be pretty much the exact same mechanism. We're going to go through it all backwards. And if we put water in, then I'm going to start leaning my equilibrium towards that ketone structure. Okay. All right. So that's the imine. So remove water, favor products, add water, favor reactants. All right. So let's look at the enamine. So something a little bit different is happening here, but it's going to be very, very similar overall. So we go ahead and look at that one. Okay, I'm still in an acidic environment. I still have an equilibrium process. Eesh, if I can draw those better. That's better. Okay, so I still have equilibrium arrows. I still have acid. So I'm gonna start off the exact same way. We're gonna protonate that ketone first. Okay, and then we can come in with our nucleophile just like we did before. So far it is all identical. Okay, just like before, once we get to this charged intermediate, we're gonna do a proton transfer. And then we're going to protonate the oxygen to make water as a good leaving group. Okay, so now we're ready. We're at the tetrahedral intermediate stage. Everything is identical so far. And we're ready to reform our carbonyl. Not really carbonyl, but we're thinking about it in the same way as like an ester or an acid chloride, where we form the pi bond, kick off the leaving group, and we get to our iminium ion. So the problem here is that in this situation, we had an H on that nitrogen, which we were able to just deprotonate and get to the imine. Here, we don't have a hydrogen on the nitrogen atom. We only have carbons. So we cannot just deprotonate it and get it to a neutral species, but it does want to be neutral. So one thing that's going to be helpful here is if we think about the resonance structure, where we have the electrons moving up onto the nitrogen. Right, that's looking closer to our final product, which let's just scroll up real quick to see it. So we have a single bond there between the nitrogen and the carbon. So we're getting a lot closer. And over here we have the pi bond, but we still have two H's there. As soon as you draw that in, you should be thinking to yourself, that looks like it could just be an elimination reaction. And that's absolutely true. That is exactly what it is. This is pretty much just an E1 elimination, where we're just going to have the water be a base, do that acid-base reaction, and we'll get to our enamine product. Okay, so it's really, really helpful to draw a resonance structure here so that you can just get eyeballs on the carbocation and say, oh, well, I can use either of those alpha positions or beta positions. Yeah, the beta hydride. So this is the alpha, beta, beta. So each of those beta positions would work in terms of giving us our final alkene or enamine product just through elimination. Okay, so hopefully you can see the similarities between the other carbonyl reactions we've done. We're really looking at getting to a tetrahedral intermediate, reforming a carbonyl. In this case, it's imines or iminium ions or enamines. But you're really looking at forming a pi bond between an electronegative atom and carbon. And for the enamine, we have the same situation here where we were losing water from this reaction. So again, if we remove H2O, we're going to favor products. If we add water, we're going to favor reactants. Okay, so it's the exact same process here. And this one, again, can also go in the backwards reaction, just doing this mechanism the opposite way. So as always, let me know if you have any questions and have a good one.